Hello everyone. So in this problem, we have a conducting loop consisting of a half circle of radius r equals 0.2 meters and three straight sections. We have the half circle only lying in a uniform magnetic field directed out of the page, and it has its magnitude given by 4t squared plus 2t plus 3 in the SI unit of Tesla with t in seconds. And then a battery is connected to this loop. It has the total resistance of the loop is 2 ohms. The first question is, what are the magnitude and direction of the EMF E induced around the loop by field B at t equals 10 seconds? So we're interested in an induced electromotive force. We know that an induced electromotive force is a result of a changing flux with respect to time. The flux is given by BA cosine theta, where theta is the angle between the magnetic field and the normal to the area. We can see here that um, the magnetic field is obviously perpendicular to the normal to the area because it's pointed out of the page, and so is the normal to the area of the loop. So the angle between them is going to be cosine 90, which is 1, or cosine 0, which is 1. So phi is just B times A. And of course, the area here is the area through which the magnetic field is passing. So we check the part of the loop's area that is lying within the flux or within the magnetic field lines. And that's not the whole area of the loop. It's just the area of the semicircle. So this is the area of the semicircle only. Okay, we know that B depends on time, but it's uniform with respect to position. So this area here is going to be constant. Now, to find the induced electromotive force, since B depends on time, then phi will depend on time as well. So this is not going to be change of time of phi over change of t. It will be instead the derivative of phi with respect to t. Now we want the magnitude, so I will just remove the minus sign and later talk about the direction separately. So this is going to be d phi by dt. Like we said, A is independent of time and it's constant, and B is uniform with position. So I can just take A outside this derivative, and we are left with dB by dt. And now we can substitute everything we have. The area is pi r squared. That's the area of a circle. We have a semicircle, so we divide this by 2. And we want to derive with time the expression of the magnetic field, which is 4t squared plus 2t plus 3. Okay, we know the radius of the semicircle. It's 0.2 meters. We just have to derive this and then substitute the time to be 10 seconds as indicated in part A. So this is going to give us pi r squared over 2, and the derivative with respect to time of this expression will be 8t plus 2. So we can take 2 as a common here and cancel it out with the number in the denominator. So this will be 4t plus 1. And now all we have to do is substitute the terms that we have here. This is 0.2 squared into 4t plus 1. And we will get a value for the induced electromotive force of 5.2 volts. This is the magnitude. We're interested in the direction as well. Now, to find the direction of the induced EMF, we look for the direction of the induced current due to the change in the flux. So we know that the magnetic field here has this expression, and we know by Lenz's law that the induced current is such that it's opposing the change of the flux. The flux here, is it increasing or decreasing? We can know from the change in the magnetic field. Now, the magnetic field has this expression, which contains terms which are all positive, and we know that t is greater than 0 and it's increasing. So B is also increasing with time. So since the magnetic field is increasing, then delta phi is increasing. Okay, and we can write here, since delta phi is increasing, I induced will oppose this increase by inducing a magnetic field into the page, because we know that the initial magnetic field is outside the page. So the induced magnetic field will be to the inside, which means that I induced by the right hand rule will be clockwise. And so will E induced as well. In part B, we want the value of the current in the loop at t equal 10 seconds. Now, if we want the value of the current, we have to relate the electromotive force to the current itself. How do we do this? We're going to check Ohm's law, because we know that this loop has, so we can check here, this loop has a total resistance that is given to be 2 ohms. Okay, so we have here that R is 2 ohms. So we can use this and apply Ohm's law to relate the induced electromotive force to the induced current and find its magnitude. Of course, when we want to use Ohm's law, we need to look for the total EMF in this circuit, because we already have a battery and an induced electromotive force. Now, since the direction of the induced electromotive force is clockwise, then it's actually going to look like this. This is E induced. And so it's opposing the electromotive force of the battery. Now we found that E induced is 5.2 volts, while E of the battery was given to be, it's actually given to be 2 volts. E induced is more than E of the battery, so the total current will have the direction of E induced. So to find the total current, we can just write I induced using Ohm's law. Sorry, we want the total current in the circuit. So I will be E induced minus E of the battery over the total resistance. So I wrote E induced minus E of the battery because I saw that E induced is more. So the total current will take the direction of the induced electromotive force. So this is 5.2 minus 2 volts, that's the voltage of the battery, over the total resistance, which is 2 also. And this will give us 1.6 amperes. So on this problem, we checked for the induced electromotive force and the induced current due to the magnetic field passing through part of a loop.